may not realise it, but we're surrounded by them. In your TV, in your stereo, your watch, car, phone, and pretty well every appliance in your kitchen. In fact, if it uses electricity, it probably has one. I'm talking, of course, about the silicon chip, the microchip. Now, making these tiny electronic brains is rather tricky. So, how do they do it? Texas, USA. Home to big stuff. Big cows, big boots, big hats, big moustaches. But Texas is also the birthplace of a miniaturized miracle, the silicon chip. And here in Sherman, 50 miles north of Dallas, is one of MEMC's fabrication facilities. In this strange, futuristic-looking plant, they produce silicon wafers, the basis for microchips. Silicon has special properties because it's what's called a semiconductor. That means that depending on how it's treated, silicon can either conduct or block the flow of electricity. It's this property that makes it perfect for supporting the millions of tiny transistors necessary for a modern computer chip. The trouble is, because these transistors are so incredibly small, the silicon base on which they rest needs to be absolutely perfect. It took decades to develop the process of producing silicon with the required perfect monocrystalline structure. They begin with raw polysilicon, or poly, and heat it to 1,420 degrees Celsius inside a special sealed furnace, which has been purged with argon gas to eliminate any air. The resulting lake of molten silicon is spun in a crucible, and a silicon seed crystal, roughly the size and shape of a pencil, and spinning in the opposite direction, is lowered into the revolving liquid. As the molten polysilicon is allowed to cool, the seed crystal is slowly withdrawn at a rate of 1.5 millimeters a minute. The result is a single silicon crystal 200 millimeters in diameter and weighing almost 200 kilograms. The silicon is so strong the crystal's entire weight can be supported by a single thread just 3 millimeters across. But it is brittle, and it must now be cut down to size without shattering. So after chemical and X-ray testing to check its purity and molecular orientation, it's fed to a silicon salami slicer. This 10-ton wire saw uses a fast-moving web of ultra-thin wire to produce wafers of silicon that are just 2/3 of a millimeter thick and 99.99999999% pure. But once cut, there are microscopic marks left on the wafer's surface. So it's time for a buff-up using a process called lapping. However, even after a twirl in this high-powered polisher, they're still not smooth enough. So they're then given yet another buff using a chemical process. The result, wafers of silicon with a surface roughness of less than 0.1 billion billionths of a meter. Buffed to a sheen, they're now finally ready for etching with the circuit design. Packing millions of transistors onto these tiny wafers is the job of chip manufacturers like Texas Instruments. It was here in 1958 that Jack Kilby managed to squeeze a single transistor onto a chip and invented the integrated circuit. Well, things have moved on a bit since then. The latest generation of chips uses almost 1 billion transistors, and according to a theory of computer science called Moore's Law, that number doubles every 2 years. But of course, if you're going to pack billions of transistors onto a small chip, then they need to be tiny. And I mean teeny-weeny tiny. But working at this microscopic scale exposes the chip makers to a major problem. When a transistor is only 1/10,000th of a millimetre across, the smallest particle of dust is enough to cause an electronic train wreck. So before staff like Dane Bailey set to work in the fab, it's on with the bunny suit.
Wafer fab stands for wafer fabrication. We build the chips here. We start with the bare silicon wafer. We run through a multitude of different processing steps. For our general product that we make here, a DSP, typically takes on the order of about 1,500 individual processing steps from start to finish.
Covering an area of just under 18,000 square meters, the fab is a Class 1 clean room. Thanks to 12,000 tons of air conditioning equipment, the air is 1,000 times cleaner than a hospital operating theatre.
There's actually less than 100 particles per cubic foot of air. As few as one particle landing on a critical area can kill a chip.
To give you an idea of how clean this room is, when we walk we produce 5 million dust particles every minute. So to avoid contamination from inadvertently dusty staff, front-opening unified pods, or FOUPs, ferry packets of wafers through the intricate process of component construction. The key problem is miniaturizing the complex designs and imprinting them onto the wafers. It's done through a process known as photolithography. First, the wafer is coated with photosensitive chemicals, which harden when exposed to UV light. In sealed dark rooms, light is shone through an image of the design, then through a miniaturizing lens and onto the coated wafer. When the chemical is washed off, the design remains, just like a developed photographic image. To pack all the components onto the wafer, they are built up layer by layer, like floors in a miniature skyscraper. The FOUPs cycle the wafers up to 40 times, repeating the photo-etching process for each new layer. Some layers are cooked, some blasted with ionized plasma, some bathed in metals. Each different type of treatment changes the properties for that layer and slowly forms part of the jigsaw making up the chip's design. The finished sheets of silicon wafer carry up to 1,000 individual microchips and over 4,000 billion circuit elements. All that remains is to slice and dice, and the journey from sand to circuit board is complete. What was once a worthless pile of sand can now change hands for up to $1,000 a gram and calculate pi to 1,000,000 decimal places in the blink of an eye. Metaphysical poet William Blake reckoned he could see a world in a grain of sand. But if he were to look again now, he would surely be even more amazed to discover 1 billion tiny transistors.
No, I can't see a thing. Ah, well, that's metaphysics for you. That's all for now, but join me next time for more fact action on How Do They Do It?